Welcome back to Deep Learning video lecture series. And this is Dr. Chiranjeevi Manike, Professor in Data Science and Cyber Security Department, MLR Institute of Technology, Hyderabad. A previous lecture, I explained a very simple code related to this single layer perceptron and multi-layer perceptron. And now in this lecture, I'm going to explain a little bit in detail of feed-forward neural network with TensorFlow. And I'll explain each and every line, and this is mainly useful to the beginners to understand the different, mainly the coding part, so that they can do some kind of experiments and they can start building this deep learning models. And then the next lecture, we will discuss mainly this, the problem of overfitting, underfitting, and how we can check whether the model is overfitted or underfitted, and what are the solutions in the next lecture. So, and this is a feed-forward neural network, and first we need to import the libraries. So I have already explained what are the libraries used in deep learning, basic libraries, and also the exclusively for the deep learning models like TensorFlow, PyTorch, and NumPy, Pandas, etc. So the first thing is we need to import the basic libraries. Like NumPy is the basic library that is for handling the numerical computations, and then the TensorFlow, that is mainly for deep learning, and there is an alternative also called as a PyTorch. So this TensorFlow mainly for building and training the neural networks. Next is scikit-learn. This is again, it's a part of TensorFlow, and this is mainly used for the data pre-processing and generating the sample data. So here these are the libraries, and this is the way we can import the libraries. Like NumPy will be imported as NumPy and with alias NP, and similarly TensorFlow, and also we have to import from the TensorFlow keras, import layers and the models. We'll see what are the layers are available under this, and also the models. Next one is a model selection, that is mainly to split the data set into the training, testing, and we use this module train, test, the split of scikit-learn under the model selection. Then the pre-processing, that is mainly to like a standardization, normalization purpose. We use here in this code, we are going to use a standard scalar. Next, sklearn data sets, because here we are going to make one classification data set, that is a synthetic data set. We are not going to use any real data set. So if you look at what are the options we have under the layers, like, and this layers module contains predefined layers, and that is mainly used to construct the neural networks. So for example, like a layer dot dense, and this is one type of like a fully connected layer. That means from one layer to another layer, all the neurons in one layer is connected to all the neurons in the another layer. It is almost looks like a denser connections. Next, with the convolution, 2D convolutional layer, that is mainly used in a convolutional neural networks that we will discuss in the coming lectures. Next, long short-term memory networks, and this is a recurrent neural network. And next, dropout, and this is mainly the regularization that we will discuss in next lecture. What is the purpose of the dropout, and also the batch normalization. Next, the models part under this model, and this module is mainly used to define and manage the neural network modules. So it provides two main types of models. One is like a sequential, that is a simple stack of layers, and then with the model that is more flexible for complex architectures like multi-input, multi-output models. Next, coming to the splitting, train, test, split. Okay, so this is a function, how it is going to split the data set into the train and the test. What is the output returned by this? Let us try to understand. So this is mainly useful for the beginners to understand the coding part from the scratch. So here you can see, and this is the original data, like on the left, it has, let us say, like attributes x1, x2, and so on, xp, and one target variable, the class label y. And this data set would be supplied as input to this train, test, split. So then it produces the 4 like this kind of data sets. So here you can see like x underscore train, y underscore train, x underscore test, y underscore test. These are the outputs produced by this train test split. So that means here, like suppose if you have specified the train test split, like split ratio or the testing 20% or 30% or 38% like that, and the data set would be randomly divided, splitted into this. So here you can see this is like, let us say like 70% of data set we want to use for training, and the remaining 30% is used for testing. So then the first, on the top, that is a training data. So this is input. These are the features, and this the corresponding outputs, that is y train. So, and this is mainly used for the training model, that is mainly in a classification type of problems like supervised training. And if you look at the bottom, there are again two, like x underscore test and y test. So in this case, and this data, this x underscore test is used to test the model, that is trained model, and it will produce the output, and then those outputs would be compared with y underscore test corresponding output, and then we will measure the accuracy. So that is about a train test split, how the data set would be split into these different parts. So next, prepare the data. So because we are going to like train the model by supplying this synthetic data set. Synthetic means it is not a real world data. So we can create the data set as like a real world. So here, by using make underscore classification from the scikit-learn, we use like here we have to specify the parameters like number of samples. So we want 100 samples in the data set, and the number of features are 20, like columns, and the number of classes under the target variable, there are 2 classes will be there. It's a binary classification problem, so 0 or 1, and the split the data into 80% training and 20% test sets. So that is a way we can use, that is 80% of the data will be used for training the model, and 20% is used for to test the model. Next, because I think in data mining and few other lectures, previous lectures, I've already explained, if the magnitude of one values dominating the rest of the attribute values, magnitude of other values, and then it deviates the the training. So for that purpose, we have to standardize that values. So here we in this code, we are going to use a standard scalar, that is to normalize the data to better training performance. Okay, so because like suppose if you take one example, if you take age as a just integer, so then, and also the salary, like age would be within the range, like suppose workforce age and their salaries in India. So like the workforce, like at let us say 19 years to some 65 years. So 19 years to 65 years, the range, the magnitude of this value, age values. And if you look at the salaries, like 15,000 to 3 lakhs or 4 lakhs like that, and the magnitude of this is completely different, it's heavy. So, and that makes, so that is to normalize such kind of data. So we use this standard scalar in this code here, mainly in the deep learning and also machine learning to pre-process the data. So for example, here you can see, like as I said, number of samples are 1000. So what do you mean by samples and what do you mean by the features? That is, you have to remember, mainly for the beginners. Here you can see, and this is a real data set, that is iris data set. So you will find in the internet, Kaggle or USI machine learning repositories. Here you can see the ID, sepal length, sepal width, petal length, petal width, and the species. So these are the features of this data set, and this is the class label. Species is the class label, and this because this is just a first 5 samples of the data set. So all the samples belongs to the one class, that is iris setosa. So here objective of my objective is to explain what is a feature and what is a sample. So this is a data set and the attributes are the features, and this is the class label species. And whereas the rows you can see here the numbered with the 0 ending 0 to 9. So each row would be a one sample, right? So that is like how. So in this case we have generated by using the make underscore classification, we have generated a synthetic data set of 1000 samples and 20 features, means 20 columns and 1000 rows, and the binary classification, that means there are only the two classes. So here the standard scalar, how it normalizes, that is it is mainly used for feature scaling by standardizing the numerical values. So it's very simple. So it transforms the data so that it has the mean, that is a mu equal to 0 and the standard deviation 1. So then the scale value of any attribute would be calculated as x minus its value and its mean and divided by sigma. So then, and this is the value, and that will be used to replace this x value, that is the standardized value. Next, here you can see here, this is the coding part. You can see make underscore classification, and the parameters we have samples, how many samples you want and how many features, and the number of classes, because it's a binary class classification problem, so there will be only two classes. And the n underscore informative is another parameter where its default value is 2. So here we subtract 15 because the 15 means the informative features. Informative features are, we can say, like strongly correlated with the target variable. Like as I said many times, all the attributes or the features in a data set may not contribute equally. So we have sometimes because of the complexity, like if the dimensions are large and the model becomes complex, and it will require huge number of computational resources and storage, etc. So in order to avoid that, and we will do some kind of a dimensionality reduction. So to remove or to avoid or discard some features, then we have to give up some kind of a ranking, the correlation, how strongly correlated, right? Based on that we would select. So here the form informative, like a 15, the top correlated, that means correlated to this target variable, would be selected. So next, the random state or the seed value, that is mainly because we use this synthetic data set and we generate the random numbers. So every time whenever we perform this, and every time it has to generate the same data set, same kind of values, and to make sure that happens, we have to set we have to use this parameter random underscore state or the seed sometimes. So that is set to any number you can give it. So that is, we can reproduce the same values again and again. Next, you can see the split into the train test sets, like 80% training and 20% of a test data. So you can see these are the values that is produced, 4 values. Train test set returns. So here you can see the x is a independent, that is features, and y is the target, and test size is 0.2, that means 20% of a test data, and is similarly the random state equal to 42. So, and this would returns these 4, like y x underscore train, y underscore train, and x underscore test, y underscore test. So it randomly select the samples, not like first 20 or first 80% of the samples are from the last 20%. It randomly select the samples. But the whatever the sample we selected, we have to select the corresponding the target label or the class label. Yeah, next one is scale the data for better convergence. Like we have to use the standard scalar, and this is a class instance would be created. Scalar is a class instance for this standard scalar class, and then we use this fit transform, that is to transform, this is to calculate these values, and then we can apply to this underscore test. So here you can see, if you want in detail, like this fit underscore transform of x underscore train and this line, this perform the two operations. Mainly first one is a fit underscore x train. It computes the mean value and the standard deviation, like as per the formula, of each feature in this x underscore train. Next one is the transform x underscore train. That means it uses the computed mean and the standard deviations to transform the x underscore train using the standardization formula that we discussed just now here. So next line, that is transform underscore test. So here we use this because here we have calculated, like at this line, like this, we have calculated the mean and the standard deviation for the training data. The same mean and standard deviations would be used for this test, that is to transform the test data set. So that is to ensure the consistency in data transformation between the training and the testing data sets. Next one is building the feed forward neural networks. So that is, so far we have done like pre-processing, generating the test data set, and then we normalize this data by using the standard normalized scalar, and we also split the data set. Now we can build the feed forward neural network. So here we define the simple feed forward neural network with the architecture, like input layer would have the 64 neurons, and the activation function used in this input layer is ReLU activation function. Next, the hidden layer. This is in this hidden layer, 32 neurons will be used, and the ReLU activation function will be used in hidden layer also. Next, output layer, that is only one neuron, because it's a binary classification. It has to produce either 0 or 1. So sigmoid activation function will be used because the values are within the range of 0 to 1. So next, so we can define the model like this, because it is a sequential layer, like the layers are stacked. So we have to select the model sequential from the models, and then dense, because from one layer all the neurons are connected to the next layer, all the neurons. So it's a dense layer, and the number of neurons as parameters we have to specify. Activation, ReLU, and input shape, the dimension, because the weight matrix need to be decided. So that here x underscore train dot shape of 1, that is input layer with the 64 neurons. And next, dense layer 32, that is a hidden layer with the activation function ReLU. And next, the last one is a dense layer with a 1 neuron, whereas the activation function is a sigmoid. This is the output layer for binary classification problem. Now let us compile the model. So let us see what are the parameters, what we are going to pass to this compile, model.compile. So we have to understand, as we discussed different optimizers, among those Adam is one best optimizer. This is mainly efficient for deep learning models. Next, binary cross entropy, that already discussed in the previous lecture. You please refer the previous lecture. That is mainly suitable for the binary classification. Next, accuracy, that is to measure the model's performance. So here the Adam, mainly why we are using this Adam here is, it's a stochastic gradient descent method that is mainly based on the adaptive estimation of the first order and second order moments. So we can compile the model. Here we have supply all the parameters, the values of the parameters, Adam, like this. And then the compile method in this TensorFlow mainly used to configure the model before training. So it specifies mainly the optimizer, like how the model updates the weight. Okay, that is why we need to use this Adam optimizer, that is to update the weights. And next, loss function, because the loss function need to be minimized, that is our objective function. So that is, the model have to try to minimize this. Next, metrics, like how the model's performance is measured. Next, train the model. Here you can see there are the parameters need to be supplied, like epochs. So number of phases through through this data, and batch size, like every time, like how many samples would be selected, like would be processed before updating the model weights. Next, validation split. From this training data, we will use a 20%, like 0.2, that is for validation purpose. So let us break down of each parameter here. So here we can see, I think I kept this point here. X underscore train, Y underscore train, that is the training input data features, and Y underscore train is the corresponding labels of the targets. So the model learns the parameters, that is X underscore train, to correctly predict the Y train. So here the epochs, if you look at the epochs, it defines how many times the model will go through the entire training data set. Okay, how many times? If epochs set to 20, then the model will train on the entire data set 20 times. Okay, and the more epochs can lead to the better learning, but sometimes it may also cause overfitting, that we will discuss in detail later. Next, batch size, that is here we have set as 32. So the model updates its weights after processing a subset, that is a batch of 32 samples. That also we already discussed. So if batch size is 32, then you can see, like if X underscore train has 10,000 samples and each epoch runs 10,000 by 32, that equal to 312.5, approximately 313 mini batches. So a large batch size leads to the more stable updates but requires more memory, that we already discussed in the previous lecture. A small batch size can introduce noise in update but may generalize better. And next, if the validation split, suppose if you set it to 20% of X train and Y train as a validation, the model will train on 80% of the data and evaluate on the remaining 20% at the end of each epoch. So it helps to monitor the overfitting by checking model performance on unseen validation data. So then let us train the model here. And what are the parameters? X underscore train, Y underscore train. Okay, that means the training data, like in the features, like x1, x2, and so on, xp in this example, and Y underscore train, the corresponding labels. Then epochs, batch size, and validation split, that is 20%, we have set. So then we have to evaluate the model. So evaluate the model performance on the test data set. So here in this case, like here this code is mainly uses the formatted string literal, like F strings, that is to display the test loss and accuracy in a specified format. So this is the actual evaluation done, and this is the output we want in that format. So that we have to specify the format here, where this 4f mainly, here you can see here point 4f, that ensures that the values are rounded to the 4 decimal places. So then we can make the predictions and convert them into the binary class labels. Because the sigmoid activation function in the output layer gives the output in terms of the probability that ranges from 0 to 1. So that need to be converted into the binary. So here, that's why we have set like 0.5, and if it is greater than, the predictions greater than 0.5, and that based on that it will be classified as either a 0 or 1. So next one is just simply saving the model, like this is a feedforward neural network which is in the format H5, and that will be saved. And if you want to load the model, like if you want to use this trained model for any other testing purpose, you can load the model. So let us quickly run this code and let us see here. So first let us, you have to check before you run this code, you have to check whether you have connected to this Google Compute Engine or not. This is a default cluster that would be allocated. if you want to run your code in the Google Colab. So first we have to import the libraries, and these are all common. Like this notebook was not authorized by the Google because I just imported this Colab from my GitHub repository, so that's why I received this one. So run anyhow. So now, and all the required libraries would be imported. It depends, like, yeah, it's a simple code, that's why it will not take much time. Next, and this is the pre-processing, so let us do it. Here we are going to create the synthetic data set, and we are going to split the data set into the train, test, splits, and then scale the data for now better convergence. So let us run this one. So we have not yet printed anything, so there is no output here. The process is done, completed. And then next one is we have to define the model. Here also, like, we have to define the model. You can see the model already created now. Next, compile the model. So once we compile the model, and the model is compiled, that is, we have set the parameters and train the model, and this is the main part. So if you train the model, you can see here epochs. We have set the number of epochs, like number of times that model will be trained on this particular data set, that is 20. That is the first epoch. It has calculated the loss and the accuracies, like all this. You can see here how this accuracy improved over, that is from one epoch to another epoch. You can observe, because it's very simple, and the number of epochs are also very small, that is 20 here, because it is executed with a very short time. So this is the way you can see here the value accuracy 91.87, because it is synthetic and it's very simple data set, so there is no surprise. So evaluate the model, that is, we have to find out this on the test data. Like we have trained by supplying 80% of the data, then we have to evaluate by giving the test data, like X text and Y test. So then that means model will predict the corresponding output of this X underscore test, and then we'll compare this Y, the corresponding label and the predicted label. Okay, so based on that, the accuracy would be calculated. You can see the test loss is 0.224 and the test accuracy is 89.50, 89%. So then make the predictions. So here we can, and the predictions, so it has made the predictions. Then you can save the model, and the model will be saved. If you go to this folder, you will be able to see that. Here you can see the feedforward underscore NN neural network .h5, and this is the model you trained on it, on this particular data set, and test it, so that you can reuse this model. And then that is the way you can reload by, if you want to reuse it, you can reload this model. So that's it. Now next lecture we will see what is mainly the overfitting, underfitting, what is bias and variance, how we can find out the model overfitting and the underfitting, how we can avoid this. Thank you for watching this video.